skipped a lot of math in the slides. I try to skip more. Okay, see what I can do. Okay. So I'm from the Network Communications and Economics lab. And this is a lab that I'm leading, and from the name you realize that we are doing interdisciplinary research. Okay, so the title of this talk is a graphical congestion game. And later I'm going to talk briefly about application to dynamic spectrum sharing. Okay, so now if you look at this short title, there are two keywords there. Actually, there are three keywords. Every word is a keyword, right? There's a congestion, and we're looking at game, and eventually we're looking at graphs. Okay, so what is congestion, right? Congestion essentially means that excessive crowding. There are multiple users, multiple players using the same resource, right? Here's a very good example. If there are many cars using the same road, there's congestion, right? People experience delays. Now, what is congestion game? So now this is a part of a Hong Kong map. Now assume that if you want to go from here, okay, for people who are not from local, this is actually CUHK. We are at this beautiful harbor. If you want to go from CUHK to the central Hong Kong to experience Hong Kong nightlife, okay, and you ask Google Map, what are the routes? What are the best way to go there? Okay, so Google actually provides you two different routes. Okay, on the left is Route 1, on the right is Route 2. Both go through highways, but different highways.
Isn't there also a train that you could take?
Yeah, yes. So I try to drive. This is not a wise decision in Hong Kong. Yeah. Now, this is a little bit small fonts. Okay, so let me tell you what that is. Google actually tell you that how long each pass is. Okay, so the first pass is actually 20. I cannot even see there, right? So it's 20.6 kilometers. Okay, so this one is roughly 21 kilometers, and it will take you 25 minutes to drive. Okay. And the second pass is slightly longer. It's 21.5. Okay, so it's 22 kilometers, takes you 26 minutes to drive. Okay. Now, if you just look at this data, immediately you want to choose the first pass because it's shorter and it's faster. And Google is now smart enough. He actually tell you, according to the current traffic, what will be the predicted traveling time on these two passes. So the Google's recommendation is actually according to traffic, if you go to the first pass, although it's shorter, you actually need to take 30 minutes to travel, taking congestion into consideration. But if you go to the second pass, although it's slightly longer, you only take 29 minutes to travel. Okay, for whatever reason. Now, in this case, if I'm a driver, I look at this updated information, I would actually go to the longer pass, but with a shorter delay. Now, if you imagine that every driver who wants to go from CUHK to Hong Kong Central will look at this information and dynamically adjust their traveling option, then essentially they are playing a congestion game with each other. Okay? And every two drivers, and actually any multiple drivers choosing the same path is going to cause congestion or delay to each other. So the question is that which one you would choose and how would the user's decisions affect the eventual delay that you're going to experience. So this is what traditional congestion game model has been looking at. Now, what will be a graphical congestion model? In a graphical congestion model, it's still a congestion model in the sense that the focus is still looking at how users' interaction will affect each other and cause congestion. The key difference is that we are looking at a graph structure. Okay? So here is a very simple example that we have a graph. And the nodes in this graph represent users, players, drivers. And edges represents the potential congestion relationship. Now, if the two nodes, for example, node 1, node 2, are connected by an edge, which means if these two drivers choose the same route, they're going to cause congestion to each other. Now, the difference is that notice that not all nodes are connected. Otherwise, it's a complete graph. It's not interesting, right? So for this node 2 and node 4, they're not connected, which means even if they choose the same routes, they're not going to cause congestion to each other. And that is the basic unique feature of this graphical congestion game.
Are they indirectly affecting each other via their connection to node 1?
Yes, that's a good point. Yeah. So the choice of 2 might affect 1, and 1 might affect 4. But there's no direct congestion.
Why?
I'm going to give you an example very quickly. Okay. So in the rest of the talk, I'm going to use color to represent a choice. And for most of the graphs I draw, I'm lazy. I just use white and black. Because when I use white, I don't need to do anything on the node, right? When I draw the graph. So here, there are two colors. You can choose either white or black. Okay? Now, what are the applications of graphical congestion? When will this happen? So one obvious example is a wireless communication. If you view these users, players as nodes, as wireless devices, when they are close to each other, and then we choose the same resource, for example, it's a channel, they're going to cause congestion or interference to each other. But if they're far away, and even if these two nodes choose the same channel, they are not going to cause direct congestion to each other, or we call interference. Thus, in another example, if you look at a rainforest, right? If you imagine the players are the animals there, and the resource they can choose are the food they want to eat. If two animals located very close by, if they are interested in the same kind of food, then they're going to compete with each other. If many animals are going to consume the same type of food, then each of them will get a very less share. But if these two animals are spread across the rainforest at very different locations, even if they prefer the same type of food, they probably won't affect each other directly. And there are other examples. Okay? So the key question that I want to answer regarding this graphical congestion game model would be the following. Since the players or the users are playing a game with each other by choosing what type of resource they want to consume, then the basic question of any game theory is that, is there a stable outcome of this type of game? Okay? And how will different nodes interact with each other, directly or indirectly? Okay? Now the second question is that if there is a stable outcome, how to reach this kind of outcome? Okay? And the last but not least, what are the properties of the stable outcome? Okay? Now here's a very, very short history about congestion game. So congestion game model was first proposed in 1973. There are almost 40 years history. And that was the model that I drew on this Google map with these two routes. And since then, that people have found tremendous applications of congestion game in biology, in politics, and in all kinds of areas, and recently in communication networking, even with the original game. Okay, there are many variations and many applications since then. The study of graphical congestion game actually was pretty recent. The first paper started in 2008. Okay? So in that particular paper, they look at a linear payoff function, which is a very special type of function, very well motivated in that particular example. And they look at the underlying graph, which are unweighted, and the edges could be directed and undirected. Okay. So in today's talk, I'm going to survey several results that we did recently on this graphical congestion game. We're going to look at a more general game type with arbitrary payoff functions, with weighted graphs, and with the directed and undirected edges. Okay, so let me very quickly talk about some prelims with hopefully limited mass. Okay, now this is the same model that we have just looked at. Okay, I'm going to use this to introduce what I mean by a graphical congestion game mathematically. We will have a set of players or users or nodes. Here we have 1, 2, 3, 4. We have a set of resources that each node can choose from. Here we have white or black. We have a graph characterizing the interaction between these nodes. In this very simple example, I'm going to use an unweighted and undirected graph. So whenever two nodes have an edge between them, then the corresponding location will be 1. So this is the first row, second column, which means that node 1 is connected to node 2. And 1, 1, 1, which means that node 1 is connected with node 2, 3, and 4. And since this is an unweighted graph and undirected graphs, then all the components will be either 1 or 0, which means either they're connected or not. And it will be symmetric, which means if 1 is connected with 2, 2 is also connected with 1. And we assume that a node is not connected with himself. So the diagonal terms are 0. Okay? And this is just a convention. You can allow all diagonal terms to be 1. It doesn't matter. It just requires a modification of the payoff function. Now, given a congestion game, and given a graph, and given the choices of the players, we can define a system state. The state just describes, at this particular moment, what are the resource choices of all players in this game. At this particular moment, the state will be white, white, black, white. Okay? Now finally, the most tricky part, which is the payoff function. Okay? The payoff function is defined for a particular node N and for a particular resource or color R. It characterizes if a player N is going to use a color R, what will be the benefit? This benefit obviously depending on the system state, depending on who is choosing which color at this moment. And to be more precise, it depends on that how many of your neighbors are choosing this particular color. Right? So in this very simple example, it's actually a linear function. For user 1, because 2 of the neighbors are using the same color white, so the payoff is -2. For this node 3, because none of the neighbors is using the same color black, so it has a payoff 0, which is the maximum payoff you can get in this particular example. Okay? Now, with this, let's try to look at first question. Can we have a stable outcome of the game? In other words, that if we allow players to choose whatever color they can choose and try to maximize their payoff for that particular color, can we reach a stable outcome? Now, if we can reach a stable outcome, we'll call it equilibrium. And in this particular talk, I'm going to focus on a special class of equilibrium called a pure strategy Nash equilibrium. This is the simplest one you can imagine. So the pure strategy Nash equilibrium, or PNE, represent a system state such that no player can improve his payoff by choosing a different color. Okay? So the Nash equilibrium is just a special type of the choice of colors by all players, such that nobody can improve his payoff by choosing a different color other than his current choice. Now, the natural question after this definition is that, do we always have an equilibrium in the graphical congestion game? The answer, unfortunately, is no. So in this very simple example, we can show that there's no equilibrium. In this example, we have 3 nodes, and we have 2 colors. However, the underlying graph structure is a little bit more complicated because it's directed. So node 1 can cause congestion to node 3 if they are using the same color, but not vice versa. And node 3 can cause congestion to node 2, so on and so forth. Okay? So when there's no equilibrium, which means that no matter which state you start with, you can always find at least one player who has the incentive to choose the different color and improve the payoff. Now let's see. In this particular example, node 1 is unhappy because he's choosing white, and also 2 is choosing white. So he has a -1 payoff. All the other 2 players are happy because none of his neighbors who can affect him is choosing the same color. So node 1 has the incentive to flip the color to black. When he changes the color, he's happy, but node 3 is not happy. So node 3 has the incentive to flip the color, and node 2 is not happy. And node 2 has the incentive to flip the color, and again, node 1 is not happy. So this can go on and on and on. Okay? So in this particular example, you can actually enumerate all possible system states, which are not many, and show that none of the system state is equilibrium. Now, of course, this is a special case, right? We will be focusing on studying the games that do have an equilibrium. Now, for the games do have an equilibrium, the question is that, in general, is it a unique equilibrium? And the answer for this is also no. And here's an example that actually has multiple equilibrium. This is the same example that we have seen before. In this case, we can see that this node 1 is unhappy because he has a -2 payoff because there are too many neighbors using the same color white. So he has incentive to change into black. In this case, he has only 1 neighbor using black color, so he has a payoff -1. And 3 also has a payoff -1, and 2 and 4 are perfectly happy because they have no neighboring using the same color. And this turns out to be an equilibrium. Because nobody can use a different color and improve his payoff. Now, this is not only one. This is also an equilibrium. If 1 doesn't change color, but 4 changes color, in this case, 3, 4 are perfectly happy, and 1, 2 are relatively happy, and nobody can improve. So later on, that we'll deal with this question in the multiple equilibrium. Okay? But in many cases, we probably don't care which equilibrium we get as long as we get a reasonable equilibrium. And obviously, for this example, you can see that if all the users are flipping color, white becomes black and black becomes white, it is an equilibrium. right? So having multiple equilibrium is the general fact. It's the truth of life, right? You have multiple solutions. Okay, having a unique equilibrium is the very, very, very special case. Okay.
So you say if you just flip all, switch all blacks and white, then you consider this another equilibrium or same equilibrium?
Another equilibrium in this case. But of course, you can relabel the resources, right? Yeah. Now, the last question is that if there is an equilibrium, how do you reach that? There are many ways of reaching equilibrium. And for the most of the talk, I'm going to focus on very special types of choices called asynchronous battery response updates. In the sense that battery response means that a user is going to choose a color that improves his payoff. And asynchronous means that we allow users to do this in asynchronous fashion, one player at a time. If two players choose at the same time, things could be messy because they could enter cycles. Okay? So one at a time. Now for this particular example, we have 4 nodes, 4 players, and it's an unweighted, undirected graph. And now everybody's using white, so everybody has a 2 neighboring interfering with them. So it has the payoff -2. So we start by allowing user 1 to change the color into 1, so you get a payoff 0. And furthermore, we can allow node 4 to change color, change white. And in this case, we reach an equilibrium because everybody is perfectly happy. There's no neighboring interfering with him. And later on that, we're going to show more examples, more possibilities of different updating rules, very briefly. Now, it would be nice if the asynchronous best response will always be able to converge to an equilibrium. This is, by the way, not always true. But if this is true, we will have a nice property called finite improvement property, FIP. It says that a graphic congestion game has a finite improvement property if every sufficiently long sequence of battle response will converge to a pure strategy in Nash equilibrium. If this is the case, you can look at any starting point of the game and let the user just do whatever they want in the asynchronous fashion, and you're guaranteed to reach something nice eventually. Okay? This is a very strong property. If this property holds, it automatically implies that there is equilibrium. Because if there is no equilibrium, it will never converge. Okay? So FIP will be the most desirable property we'll look after. Okay? If FIP doesn't work, we'll try to see whether there's equilibrium or not. So let me summarize the 3 questions that I have mentioned before using the terminologies that I've just defined. When will a pure strategy equilibrium exist? And even stronger, when does an FIP hold? And finally, what are the properties of this pure strategy equilibrium? Okay, so this will be the prelim. And for the rest, I'm going to gradually look at the different types of graphs and see what kind of results we can get. Okay, and the rest of the results will be a very brief survey from a couple of different papers. Okay, so let's first look at unweighted, undirected graphs. This will be the simplest case. Okay, so this is a joint work with my postdoc and the collaborators from University of Michigan. Now, before going through the giving you the examples and the graphical illustrations, let me remind you of the default assumptions. Because later on, for each type of the game we're modifying one or multiple of these assumptions. The default assumption is that we are looking at a game with arbitrary number of players and resources. Okay? That could be white, black, green, yellow, blue. Okay? And so the payoffs can be resource specific, which means different resources can offer different benefits. Example, in wireless communications, if the resources represent channels, different channels can have different channel bandwidths. A larger bandwidth can offer you higher data throughput. Right? Now, payoffs are also player-specific in the sense that different players can achieve different payoff on the same resource, even experiencing the same congestion level. Right? Looking at the same channel, if you have a better channel gain, I have a worse channel gain. So you will receive the higher data rate. I will receive a lower data rate. Okay? Very good. So now let's first look at the strong property, right? Existence of finite improvement property, which implies the existence of equilibrium. The first class of game that we can show this strong property is the game where there are only two types of resources. They can be white and black, or they can be on and off. Now, imagine on and off. If I turn on, I transmit, I spend some energy, and I also get some data rate in return. If I turn off, I lose some of the throughput, but I also don't consume my energy. So there's a trade-off. And if this is the case, then essentially we are looking at a distributed scheduling problem. Right? Tony has talked a lot about scheduling. This is a very simple, naive way of doing distributed scheduling. Okay? Depends on how you define the payoff. It could be closer to reality or very abstract way. Okay? So essentially everybody choose either on and off depending on their neighborhood. Yes?
Do you assume monotonicity in the payoff?
Yes, yes. The payoff has to be monotonically non-increasing in the congestion level. That's right. Yeah. Thanks. That's very important. Very, very important. Yeah. Congestion is a bad thing. Okay. Okay. So this is the first case. We modify this resource. Need two resources. And the second case is that if the resources are homogeneous, not necessarily two, could be more than two, we also have this finite improvement property. Example, in a wireless communication, if the channels have the same bandwidth, and for example, in OFDM, that these channels are logical channels, are interleaved based on the so-called subcarriers. If you do this interleaving, you can actually achieve frequency flat fading across these logical channels. Now, if this is the case, the resources are homogeneous. For one particular player, I choose white, yellow, green, black. It doesn't matter. They all offer me the same throughput function if they experience the same congestion level. But payoff can still be player specific. Different users can experience still different data rates. If this is the case, then we also have the finite improvement property, and that's the equilibrium. Now, the common proof idea across these two cases is for people who are familiar with game theory or familiar with dynamic stochastic optimization, then essentially construct potential functions similar as the Lyapunov function. And you can show that if the user are going to do their battery response updating in an asynchronous fashion, whenever one user updates its response, the potential function is going to decrease a little bit. Whenever another user updates, it's going to decrease a little bit either, as well. So eventually, this potential function is going to be monotonically decreasing in users' battery responses, and it's lower bounded, and it will definitely converge. And once it converge, which means nobody can perform any battery response anymore. And by definition, it is an equilibrium. Okay? So this is the key idea. Now, of course, that life is not so nice, and in many cases, we don't have this FIP. Now, let's take one step back and see, assuming that we're not that aggressive, we just want to look at when do we have equilibrium. The first example of guaranteed to have equilibrium is tree. Okay? How do we prove that? The key idea of proving tree always has an equilibrium is if you first look at a smaller graph and assume this graph always has an equilibrium. And now you add additional node to this graph and only allow this node to interact with one node in the smaller graph. And in this case, you can show that no matter what will be the payoff of this new node, what will be the payoff of this original node, after adding this node, you can always modify the color choice of the existing smaller graph if necessary in order to reach a new equilibrium. In other words, that if you have a smaller graph with equilibrium, you can add this node one by one connection at a time, to ensure larger graph also has an equilibrium. So through induction, that one node always has an equilibrium. And by doing this, any tree will have an equilibrium.
Not necessarily. So here there's no congestion. But are you saying that in a tree there'll always be an equilibrium with no congestion? Because that's the example?
Will be arbitrary congestion. In this example, it's just no congestion, but it's just a special example. Yeah. Okay. Good. The second example that always has an equilibrium is a loop. And the key idea of proving loop always in an equilibrium is first, let's make a cut here so that the loop becomes a line, which is a special case of a tree. In that case, you will have an equilibrium. Now the difficult part is to put this edge back. If you put this edge back, become a loop again, in the most fortunate case, that nobody will change their color and you automatically get an equilibrium. But in the worst case, the single edge can have a ripple effect such that everybody wants to change their color. So you need to go through all kinds of possibility to see that putting this edge will not mess up with the original problem. And in fact, we can do that. So any loop has an equilibrium. The third example of having an equilibrium is a complicated example, but it's the simplest in proof. It's a regular bipartite graph with the non-player specific payoffs. A graph is regular means that every node has the same number of connections. In this graph, everybody has 3 connections. It's a bipartite means you can divide the nodes into 2 groups and associate one group with a letter called A, associate the other group with a letter called B, and you look at the edges, no 2 users from the same group will be connected. So you can associate one group with black, one group with white, and no white nodes were connected, and no 2 black nodes will be connected. So this is bipartite. And the last condition is that payoffs are not payoffs are not player specific. In this case, there's guarantee have an equilibrium. And the simplest case, if white and the black resources are equally preferred by users, then you just ask one group to choose white, one group to choose black. And that's automatically equilibrium as shown here. And of course, there will be another occasion where the white color is so good that everybody wants to choose white despite of the potential congestion you're going to experience. In that case, let it be. Everybody choose white, and that will be another equilibrium. So this is a complicated graph, but the proof is the most straightforward. Okay, good. So now I'm done with the unweighted, undirected graph. I'm going to move into the more difficult case of the weighted graphs. And as you can see, a lot of the results and proof ideas in the unweighted case will be generalized to this case. Let's first focus on the weighted but undirected graph. And here's an example. The still familiar 4 nodes, 1, 2, 3, 4, same topology. A difference is that we have weights on these edges. Okay? And later on in the wireless communication example, that we can show that its weights, for example, depends on the transmission power of the nodes. So in this case, since this is undirected, the corresponding S matrix here is a symmetric matrix. If I have weight with you and you also have weight with me, and it's the same weight. But the components is no longer 0, 1. It's 0 and any positive number. Here I have integers, but it can be real numbers. Now, what will be the results, right? Let's first look at what would be the case where the weighted undirected graphs we have the finite improvement property. And it turns out that we have exactly the same result as before in terms of the group conditions, right? We have 2 cases. Case 1, only we have 2 resources. And case 2, you have homogeneous resources. But keep in mind that we now allow weighted graphs. So this generalized result in the unweighted case. And the proof is slightly different because previously, when you construct the so-called potential function, the potential function takes integer values because these weights are actually 0, 1 in the previous case. Now, in this case, the weights are arbitrary, so the potential function can take arbitrary real functions, real numbers. So showing that the potential function is monotonically decreasing the lower bounded is not enough to show that the convergence happened in finite steps. You need to do something a little bit different. Now let's focus on the case of homogeneous resources, which is one of the 2 cases that I just mentioned, and look a little bit deeper into the property of the equilibrium. So we have 2 kinds of properties. And number 1 is that when the resources are homogeneous, when all the channels have the same bandwidth, you can actually predict what would be the maximum congestion level a user would experience at the equilibrium. This maximum congestion level will be the summation of the weights connecting with your neighbors divided by the number of colors you can choose. Imagine that you are in a very crowded area. Everybody around you is transmitting with higher power. In this case, that you are going to experience heavy congestion no matter which color you choose, no matter which channel you choose. But the more channels you can choose, you do have more freedom to avoid congestion. So it will be the summation of the interference you can potentially receive on all channels divided by the number of channels you can choose. Okay? So in this particular example, that for player 1, it is interfering with player 2, 3, and 4 with these possible congestion. So you sum them together, divided by 2 colors you can choose, and this is the maximum congestion level you will experience. And this also applies if different nodes can choose the different number of colors. You can choose 2 colors, I can choose 5 colors. The second property is that in this case, since the resources are homogeneous, in general there are multiple equilibrium. Okay? Whenever you have homogeneous users or resources, that you increase the probability of having multiple ones. Now, if we are interested in finding the best equilibrium that maximizes the payoff, it turns out that this problem is NP-hard, which means that try to study the best one or the worst one among all the equilibriums you're going to experience in general is a very hard problem. Forget about it. Okay? Now, enough for this. So now let's follow the same route to look at a case where the finite improvement probably doesn't exist, or we don't know whether it exists or not. We only want the pure strategy Nash equilibrium. What are the possible cases? The first case is a generalization of the tree, but here is a directed weighted tree. What is a directed weighted tree? The left is an example. In this tree, if you remove all the edges, arrows, and to the corresponding undirected case, if that is a tree, then we call the original one a direct weighted tree. An idea of proving that equilibrium exists in directed weighted tree is the same as before. Put one node at a time, even if it's directed, even if it's weighted. The idea still works, although it's more tedious proof. The second class is quite interesting. Doesn't have a similar one as before. It's a directed acyclic graph. So here's an example. It's directed and it's acyclic, which means there's no loop in the graph. Why this is a nice graph? Why this is a nice class of game? The reason is that if we have a directly acyclic graph, we could create a so-called topological sort by rearranging these nodes from left to the right in a way that the edges will only go from left to right, but not the other way around. So this is guaranteed by the fact that there's no loop in the original graph. So you can reorder that. And this is completely equivalent of this. It's just by massaging the node and the position of these edges. Once you can do that, then you can actually easily construct an equilibrium directly. You allow the first node to choose whatever color he wants, and then a second node, third node, and a fourth node. And since the edges only go through the right, so a node's choice will only affect the later nodes, but not affect the previous node. In other words, that whenever 2 makes a decision, 3 will not change its original decision because 3 is not affected by 2, and so on and so forth. So through only n steps, you will be able to create a pure strategy Nash equilibrium. Now, this is a summary of the results for the weighted game, right? For the weighted graph, either directed to undirected. There are some results, but you might fear that the results are limited because they only look at very special cases. And indeed, they are limited, but they are not as limited as you thought. Because by combining multiple proof techniques together, you will be able to understand more complicated graphs. For example, this graph is not a tree. This graph is not a directly acyclic graph. But using the previous idea of adding one node at a time and creating topological sort, you will be able to prove that this complete graph actually has at least one pure strategy Nash equilibrium. Okay, so let me come back to the other part of my title, which is what is spectrum sharing. Okay, how will the study of this graphic congestion scheme help us to understand the wireless communications, help to understand how users are going to choose channels and avoid each other and best utilize the spectrum? So when we talk about wireless, we need to talk about the interference model, right? So there are two types of interference model. There's a protocol interference model, and there is a SNR-based physical interference model. Since we are talking about a graph, then very naturally, we will think about the protocol interference model, because this is indeed a graph-based model. In the protocol interference model, in the simplest example, that the two users in the wireless network, we have the pairwise relationship. Either we interfere with each other, or we are not. So if you translate into a graph, that will be an undirected, unweighted graph. Either we have an edge connected, or we are not. Now, if you go a little bit further to look at a case where the users have different transmission range, for example, here we have a 3 pair of nodes representing 3 users. The first pair of nodes has a larger transmission range, and the second pair of nodes has a smaller transmission range. So the first node can generate interference to the second node, but not the other way around. So in this slightly more general case, we can use the unweighted but direct graph to model the interference relationship between nodes. And we know that once we translate into graphs, and once we utilize the data rate as the payoff function, we can utilize the theory that we just developed to understand how users choose their channels. Now, let's try something really challenging. The physical interference model. The physical interference model fundamentally is not a graph-based model. It assumes that everybody is interfering with everybody in the network. There's no 0 or 1. There's only difference of degree. And in particular, that the data rate of the payoff of a user choosing a particular channel will be increasing function of the signal to interference plus noise ratio, which depends on the weighted interference you receive. And this interference is weighted and asymmetric because it depends on who are your neighbors, who are the interferers, what will be their transmission power, and how far they are. Okay? So it's weighted, it's asymmetric, it will translate into a directed and weighted graph. And in general, it's a complete graph. Everybody is interfering with everybody. Now, in this particular example, in this particular case, will the theory that we just developed help us in any sense? So let's take a look at an example. So this is the example that we have a square area with air by air meters, square meters. And we're going to randomly place the nodes inside. We're going to randomly place the uniformly place the transmitters. And we're going to place the corresponding receivers randomly around their transmitters. So the receiver cannot be too far from the transmitters. But transmitters are arbitrary position. Okay? We allow that each node, each transmitter has a fixed transmission power, 100 milliwatts. No worry about power control. And the channel bandwidth is the same and have frequency selective fading, so it's a homogeneous resource. And the user's payoff is equals log 1 plus SNR, it's a data rate. And the channel gain follows distance-based for the simulation purpose. Now, what will be the property of this graph? Okay. Now, if you look at the general setting, as I said, this is a weighted graph because the interference is weighted. This is a directed graph because I can generate interference to you. You may not generate too much interference to me. And also, oops. And also, this is a graph with loops, right? If I generate interference to me, I have an arrow pointing to you. You generate interference to me as well. You have an arrow pointing to me. We have a loop already. And in general, it's loop everywhere. So for this general graph structure, there's nothing we can say. The Nash equilibrium may not exist. We don't understand. However, if you allow the network size to change, if the network becomes larger and larger, and keep in mind that the receiver must be around this transmitter. If the network becomes larger and larger, then each of the transmitter-receiver pair will behave more like dots in this larger network. Instead of transmitter-receiver spreading all around, that you have n pair of transmitter receivers more like behaving as n dots in this network. In this case, the graph actually becomes undirected and weighted. It's undirected, which means if you generate interference to me, I definitely generate interference to you because it's just between two different dots. And it's still weighted because it still depends on distance. And furthermore, we assume that the channels are the same, so it's channel homogeneous, resource homogeneous case, and then we know from theory that there exists a pure strategy Nash equilibrium for this game. And actually, this game has a stronger property, which is the finite improvement property. So let's see how it works in simulations. So here I'm plotting the different lengths of the network size. Okay, so the network unit length, one side length could be 50 meters to 500 meters. And for each of the network size, I'm going to choose 10 different randomly generated topologies. And for each of the generated topology, I'm going to use asynchronous best response updates to see whether such sequence of response updates will converge to an equilibrium or not. Now, if this convergence happens beyond 1,000 time slots, I don't want to wait. Because in that case, I don't know whether it will converge or it takes too long to converge. So only on the case where the convergence happens within 1,000 time slots. So these are the dots represent the convergence time for different realizations. There's a total of 10. When the network size is small, 7 out of 10 realizations converge. And the convergence time can be very high. But now, when the network size becomes larger and larger, actually the convergence time becomes smaller. It's faster for users to organize into equilibrium. And also eventually that all 10 topologies regenerate equilibrium. So this verifies our intuition that when the network size is larger, that the graph structure changes and the theory has a better prediction power. This is a similar graph actually under the similar simulation, but I'll give you a little bit different perspective. This is still the change of network size. And here we're plotting the percentage of so-called fast convergence. So instead of waiting for 1,000 time slots, I only wait for 500. I look at what will be the percentage of the topology that allow fast convergence. With small network size, only 40% of the topologies allow fast convergence. But when network size becomes larger, eventually that all the topology will allow fast convergence. The same graph I showed before, but here I want to emphasize this is not only a randomly generated graph, but this is also an equilibrium resource choice. So here we have 5 different colors representing 5 different channels: blue, green, black, pink, and red. And as you can roughly see by immediate first glance, that users tend to use different colors at different places. They tend to not cluster the same colors at the same location in order to avoid interferences to each other. Okay, so in the last couple minutes, I'm going to briefly talk about several variations that we have been doing beyond the models that we've been looking at. Okay, there are actually many, many variations you can look at. This is very simple. This is very preliminary start. The one variation is that you can allow so-called non-singleton games. In the previous example, we have all implicitly assumed that one player can only choose one resource at a time. Now, this is not necessarily the case in practice. In particular, in the so-called non-singleton game, a player may be able to choose multiple resources at the same time. This player is choosing 3 colors at the same time. This player is choosing 2 colors at the same time. If you look at wireless communications, a user maybe have the capability of transmitting over multiple channels at the same time. And the payoff will be the summation of the data rates you get over all channels you choose. And under this setting, we look at a different set of games. And there's one particular interesting class of game called power set graphical congestion game. In this case, everybody has the same set. Everybody has 3 colors to choose. And everybody can choose any subset of the 3 colors at any time. You can choose 3 color, 2 color, 1 color. Okay? This is called a power set congestion, graphic congestion game. And we can show that each power set graphic congestion game on the unweighted, undirected graph has the pure strategy Nash equilibrium. However, it may not have the finite improvement property. Now, this leads us to think the following question. It doesn't have the finite improvement property. What does it mean? Does it mean that allowing people to self-organize may not converge? Or maybe means that the updating rule is not good enough? So this motivates us to look at a different updating rule. So far, we have considered better response, where that users will choose a color or choose a subset of different colors to improve its payoff. Instead, we restrict people to look at best response. You cannot choose any new resource choice. You must choose one that maximizes your payoff, given the existing choices of other users. We actually go one step further. We actually limit you to be lazy. We call lazy best response. For example, if currently use color red, now you have two ways to improve and maximize your payoff. You can use color red or blue, or you can use color green and blue. In either of these cases, it will maximize your payoff. But I require you to be lazy because the first case, you only add one color in. That's good. In the second case, you remove the existing color, add two new colors. That you're doing too much. So the conclusion is that lazy is actually good. If you are lazy, then any power set game on an unweighted and undirected graph can reach a pure strategy Nash equilibrium by polynomial number of lazy best response. The final variation that we can talk about is the generalization of the payoff functions. So far, all games that we look at assume that your payoff is a decreasing function of the congestion level, and the congestion is a weighted sum of the congestion from your neighbors. But if you look at the wireless networks, this function of a weighted sum may not be the general form. For example, if you look at a random access network, then people are interfering with each other using this product form according to the probability, instead of the function of the weighted sum. And in this particular example, we can actually construct a special potential functions to show that the game also has a finite improvement property. Okay, so let me summarize. The graphical congestion game is a powerful modeling tool for many things, and in this particular talk, we look at wireless communications. But as I mentioned very early on, it has many other applications. But research in this area only started in 2008 and still in its infancy. In fact, there are many, many open problems that we can look at. For example, what would be the existence of equilibrium and FIP for more general payoff functions and graphs? We only know very little, right? And what are the properties of the NEs? We actually know very little about it. The converging speed to PNE, we have some understanding, but things could be faster. And thanks to the previous speaker, we can look at dynamic graphs as well, right? If the graphs change faster, then you can switch resources. What would be the best way to switch resource, predicting the change of graphs? Okay? So these are some of the papers related to this talk. And thanks a lot.
What about randomized strategies?
Randomized strategies lead to mixed strategy equilibrium. And actually, for game with finite number of users and a finite number of resources, there always exists a mixed strategy Nash equilibrium. Yeah, so that would be good. So this is actually one of the most positive results, but I didn't put it here. And the reason for focusing on pure strategy Nash equilibrium is that pure one is easier to implement, so you don't have to worry about randomized. If you have the capability of randomized with no overhead, then things will be much nicer.
Yeah, I have a few questions actually. First one is anything known about approximations of the social benefit?
Approximations about?
Approximations of the game value.
Of the game value, of the optimal. It's not clear to me in this class of games. This is really a new class. As I said, that we try to look at the best strategy, the best equilibrium. The equilibrium gives you best performance, but that turns out to be an NP-hard problem. For some special class of this game, for example, when the user has a payoff of 0 and 1, when it experience a large congestion, you have a payoff of 0. When you have experienced small congestion, you have a payoff of 1. In that case, we have a better characterization of the performance of the equilibrium. But in general, it's actually quite hard.
Yeah, so another one is Has something been done regarding restricted payoff functions, say convexity or some sort?
It has to be decreasing. It doesn't have to be convex. Yeah.
Right.
So there's no convexity concavity constraint.
Right. But are there any cases where it helps to use, let's say, if you look at your example with the wireless case, you have different kinds of a payoff function. Is there anything known about it that if that would help in the solution?
The first paper that I mentioned in 2008 looked at linear, so you can say more in that case. We have not looked at general convex or concave, but I said we look at binary case very recently, actually these couple of days, and we can say more, yeah. But we haven't looked at the general case yet.
Any other questions? All right, let's thank all the speakers.
Okay, thanks.